going to take a look at some of the special cases in three variable systems of equations. The normal case, which is where we're able to get the matrix into a perfect row echelon form, has one solution, and that one solution can be thought of as the intersection of three planes. Linear equations in three variables are equations of planes. So like a wall or a floor or a ceiling. So the normal case is where we get one solution when we put everything together. You can see that these three planes all intersect in one point. If we recall from 2 by 2 systems, we did have some special cases which we called inconsistent and dependent. So just a quick little reminder, with the 2 by 2 systems, inconsistent was parallel lines, right? And they never intersect. And this had no solution. Dependent was when we draw two lines and they turn out to be the same line. This had an infinite number of solutions. We're going to see both of these cases show up in a 3 by 3 system of equations now, but they are not exactly like they are in two variables. So first of all, the case that we call inconsistent does still have no solution, but there's a few ways that this could work out. One possibility is that we have three parallel planes. That's the analogous thing to two parallel lines, three parallel planes. But that's not the most common situation, and that's the easiest to spot because all three of those equations would have to follow very similar patterns for that to work out. What's more common is something like this, where we can see that if you imagine sending a line down the center of this, and that line would have to, let's draw that again. That line would disappear right about here and then show up again here if I were sending it down the center of this configuration. All three planes might be perpendicular to this line, or rather parallel to this line, without being all parallel to each other. You can see that even though there are lines of intersection between any two planes, so this is a line of intersection, here's another line of intersection, and here's another line of intersection, they don't ever all three intersect anywhere. And so in all of these cases we get no solution. And the way we recognize that in a matrix is that when we're trying to get row echelon form, we accidentally get a row of all zeros on the left and a non-zero number on the right. This will make more sense once we've seen it happen. The dependent system could, again, it could be all three planes actually being the same plane, but that's not the most common case. The most common case is where we get a solution set like this, where all three planes intersect not just in a single point, but in a line, and a line has infinitely many points, and therefore we get an infinite number of solutions in this case, just like we saw with the 2 by 2 system. So this is an infinite number of solutions. And the way we recognize a dependent case from a matrix is that as we're trying to get it in row echelon form, we end up with a row of all zeros, including the number on the right also being a zero. So let's take a look at some systems of equations, make them into matrices, and start trying to solve them by Gaussian elimination in order to see what happens. Before we go to a system of equations, though, we're going to look at one that has already been put in row echelon form. We try to get ones on the diagonal and zeros below in trying to get ones on the diagonal, this zero, or actually in trying to get one of those other zeros, this zero just sort of happens by accident. The fact that we can see in this matrix our bottom row turned out to be all zeros is our clue that this is a dependent system. So the first step is to recognize it. However, this is where it differs from the 2x2 case. Maybe in the 2x2 case you're happy enough to just say it's an infinite number of solutions. Here we can do a little bit more, and we're required to do a little bit more. We can still express that solution set using a parameterization. The way we do that is first just reading off the equations. So that's x minus 2y minus 8z equals -4, and y plus 5z equals 2. Now, we're not going to be able to get an ordered triple, but what we can do is say, let's just let z be any real number and express both x and y in terms of z. So what we do is this. I'm going to just solve this bottom equation for y in terms of z. To do that, I would subtract 5z from both sides. And that gives me y equals 2 minus 5z. Now I'm ready to take this and substitute it into the original equation just like I would if I had a number to plug in, but instead I'm plugging in a variable expression. So that this whole equation now becomes x minus 2 times y, but y in this case is 2 minus 5z. I have to put it in parentheses. Since y is multiplied by 2, really this whole expression needs to get multiplied by 2. And then keep the rest of the equation as it was. And I need to simplify everything out and solve it for x. This is going to give me x in terms of z. So this becomes x minus 4 plus 10z, just distributing into those parentheses, minus 8z equals -4. Combining these two terms, I get, and let's go ahead and add 4 to both sides also. It just happens to drop both of those terms out in this particular case. I can see that I get x plus 2z equals 0, and so subtracting 2z from both sides gets me that x is equal to -2z. So I'm going to write this as an ordered triple. X is -2z, y is 2 minus 5z, and z is itself. I will leave that as a z. The meaning of this solution set is that for any real number z, I could plug it into all three of these, and it would give me an ordered triple that is a solution to the dependent system of equations. Since I have an infinite number of real numbers, z, to plug in, I get an infinite number of ordered triples that are solutions to this system of equations. So keep in mind that with a dependent system of equations, we don't stop as soon as we've recognized that it has an infinite number of solutions. We need to keep going until we can express it parameterized like this so that we know what that solution set looks like. And now we'll take a look at a system of equations that we start from scratch without necessarily knowing that it's going to turn out to be a special case. As I'm drawing up my matrix, one thing that I'm allowed to do just to save a little bit of time is if I notice that I have a 1 showing up in an equation that is not the first one, I can go ahead and swap the order of the equations, kind of like swapping 2 rows in a matrix before starting to write it, just so that I don't have to write the whole matrix over again. So I'm going to put this middle equation in the top row, 1, 2, -1, 2, and the top equation in the middle row, 2, 5, 1, 8. And the bottom equation stays where it is. Notice that it's missing a z term, which is why we want to fill in a 0 for that z. It's missing a z term. That has nothing to do with the fact that it's a special case. Any equation can start out missing any term. So we have this now with our 1 in the upper left corner. So the first thing we want to do is get zeros below it. And the kind of transformation that's going to work for us is negative, so let's draw this bracket here and show where we're aiming. -2 times row 1 plus row 2, and -3 times row 1 plus row 3. So let's just try to do these without writing out what the transformations are. If you find that it helps to write out the transformations, the calculations off to the side, then by all means do so. But if you're able to do these calculations in your head, then it will save you some time. So, -2 row 1 plus row 2, that's going to be -2 plus 2 is 0. And then -4 plus 5 is 1. And then +2 plus 1 is 3. And then -4 plus 8 is 4. For the bottom row, I have -3 plus 3 is 0. -6 plus 7 is 1. +3 plus 0 is 3. And -6 plus 5 is -1. We can already notice some similarities between these two bottom rows, but we'll keep going until it looks exactly like what we're expecting it to look like in order to identify it as inconsistent. We're now looking at the second column. Again, we see that the 1 is already in place for us by luck, so we will go for the 0 below it, and the transformation that will do that for us, this is going into the bottom row now, is simply -1 times row 2 plus row 3. And you really could multiply either row by -1 in order to do this. So that will look like, basically I'm doing row 3 minus row 2. So 0 minus 0, 1 minus 1, 3 minus 3, and then -1 minus 4 gets me -5. Then I'll go ahead and fill in the other 2 rows. Okay, so here's what we see. We were only trying to get a 0 in this location, and that would be here, but we accidentally got a 0 here too. It was just set up to happen that way. We couldn't make that happen, but it did happen. So that what we have in our bottom row now appears to match the description of an inconsistent system, where we have all zeros and then a non-zero number on the right-hand side. The reason that this corresponds to an inconsistent system, we could see by writing out what that equation would look like. That would be 0x plus 0y plus 0z, so that's on one side all 0, equals -5. And we can see that that's a contradiction. It's not possible to satisfy that equation. That's why this is the no solution case. And the name we give to our no solution case in systems of equations is inconsistent. Now, the nice thing about these inconsistent systems is because they don't have a solution set, there is nothing to express. It would not make sense to go and parameterize a solution set like we did with the dependent system. So that one had an infinite number of solutions to express. This has nothing. So once we have recognized this one, we're done with it.